Good evening, students. Today we have come again to learn more about data representation in computers for class 11, Uni 1, Chapter 2, Computer Science. See, today we learn representing unsigned integers in binary. Representing unsigned integers in binary. Actually, what happened? In computers, we can do so many type of calculations on numbers, even on decimal numbers. We can add, multiply, divide, do complex calculations, so many types of calculation we can do. Now, if we think how it can be done inside the computer, as computer can understand only 0 and 1, on and off. Okay, how it can work with decimal numbers. Today we will learn all those things here. See, we are going to represent integers in binary. Integers means decimal integers or unsigned decimal integers. See here, an unsigned integer can be either a positive integer or 0, but never be a negative. Unsigned means if there is no sign in a number. Suppose 6 is written. Suppose the number 6 is written, then this number is considered a positive number. Means plus is there. Okay, plus is available there. Okay, and whenever we write 7, suppose 7, this cannot be treated as -7, because to have a -7 we have to write this minus symbol before the 7 number. So a number, unsigned integer, if sign is not there, then that number must be considered as positive integer or 0. Okay, and never be a negative number. For example, in a single decimal digit, we can write a number between 0 and 9. The largest number is 9. In 2 decimal digits, we can write a number between 0 and 99. Largest number is 99. In 3-digit decimal numbers, we can write a number between 0 and 999. The largest number is 999, and so on. We can go like this. Now, since 9 is equivalent to 10 to the power 1 minus 1. 9 is equivalent to 10 to the power 1 minus 1. How it is possible? See, 10 to the power 1 minus 1, okay, is equals to how much? 10 to the power 1 is equals to 10, and minus 1, then it will become 9. So 9 can also be written as like this. 9 can also be written as like this. Similarly, 99 can be written as like this. And 999 can be written as 10 to the power 3 minus 1. Okay, and so on like this we can write. Similarly, for n decimal digits, we can write number from 0 and 10 to the power n minus 1. N decimal digit 10 to the power n minus 1. Okay, so this is the formula we have developed to represent the largest number in total number of digits. Okay, suppose we are going to take total number of digits 5. Okay, then what happened? 10 to the power 5 minus 1 will be the largest number. Okay, that is 9, 9, 9, 9, and 9. This will be the largest number. 10 to the power 5. So this is the formula we have developed here. Now, analogously, in binary number system, an unsigned integer containing n bits can have a value between 0 to the power n minus 1. It means in binary number, in decimal number, the base is 10. Base is 10 for decimal number. Whose number? Decimal number. Okay. And for binary number, base is 2. Okay, for binary, this is like this. This base 10 for decimal and base 2 for binary numbers. So to represent binary number, The largest number, if we want to obtain from a n bits or n number of digits of binary numbers, then 2 to the power n minus 1 will be the largest number. So we can say from 0 to 2 to the power n minus 1 will be having the different values. It's not different values. Okay, you can understand like this. For 1, okay, 2 digits. Suppose 2 1 1 is, we have taken 2 digits in binary. In binary we have taken 2 binary digits. Okay, 1 1. This will be the largest number in binary, which is equivalent to the power 2 minus 1. Okay, 2 to the power 2 equals to 4 minus 1 is equals to 3. Okay, 3 it is in decimal system. If we convert it in binary, then it will become 1 1 in binary. Okay, so 1 1 is the largest number in binary number. So the formula is, hence n bit pattern can represent 2 to the power n distinct integers, 2 to the power n distinct integers. An n bit unsigned integer can represent integers from 0 to 2 to the power n minus 1. Understood? Total this number of digits, okay, we can obtain using the binary equivalent. Example, here we have taken total 8 number of digits, 8 number of bits, binary bits. Okay, so from 0 to 2 to the power 8 minus 1 up to 255 it will give, which is equivalent to 255 is equivalent to 8 1 1 1 1 1 1 1 1 1. This will, if we convert this is in binary, if we convert in decimal, it will become 255 in decimal. So a binary digit, total 8 bits. If 8 digits of binary bits we have taken, then it will give from 0 to 255, 0 to 255. Similarly, if we are taking 16 bit, then it will give 0 to 65535. If we take 32 bit, okay, then it will give total 9 plus digits, and if we take 64 bit, then it will give 19 plus digits, 0 to 19 plus digits. Okay, this much it is going to give you the numbers. This way, in this way we represent. Thus the unsigned integers are represented by storing their equivalent binary code through n bits, where n can be 8 or 16 or 32. That's binary addition. As we know that computer don't directly work upon decimal numbers, so we have to perform decimal addition using binary addition. See how it is done internally using binary addition. To do binary addition, there are 5 rules, total 5 rules of binary addition. ALUs or CPUs or computer don't directly work upon decimal numbers, rather they process binary numbers, as a computer can understand only binary numbers. Okay, so here we are doing binary addition to understand that how computer internally processes all those binary additions. See, the basic rules are, the 5 basic rules of binary addition are like this. If we add 0 to 0, it will become 0. If we add 0 to 1, then it will become 1. If we add 1 to 0, then it will become 1. Okay, and if we add 1 and 1, then it will become 1 0, not 2. Okay, in decimal 1 plus 1 equals to 2, but in binary it is 1 0, because if we convert this, it is in decimal digit, then if we convert this in binary, it will become 1 0. You can convert it. Okay, so 2 will become 1 0. 1 plus 1 is equals to 1 0. We have to remember this. and if we add 1 plus 1 and 1, then it will become 1 1, not 3. Okay, because 3 in decimal is equivalent to 1 1 in binary. Okay, so if we add 3 1, then it will become 1 1. If we are doing addition and this case will come, then what we have to do, if 1 plus 1 is has to come, then we have to write 0 there. In that column we have to write 0, and we have to carry 1 for the next column. And if we are finding 3 1, then it will become 1 1, but we have to write 1 and we have to carry 1 for the next column. We will see this in example here. Adding binary numbers just like decimal numbers. Adding binary numbers just like decimal numbers. See, the binary number are also added column by column just like decimal numbers. Also, the way results larger than largest decimal digit are carried over in binary addition. Similarly, results larger than 1 are also carried over in binary numbers also. Okay, it is similar like decimal numbers. For example, here binary adding 1 1 1 1 4 1 with 1 1 0 1 1. See here, we have obtained an equivalent also. 1 1 1 1 will be equal to 15 in decimal, and 1 1 0 1 1 will be equivalent to 27 in decimal. And now we are adding here. See, from rightmost side we have to do like this. 1 1 will become 1 0, so 0 we have written here, then 1 we have carried forward here, then 3 1 it has come here, then it will become 1 1. 1 is written here and 1 is carried forward here, then again 1 1, then it will become 1 0. 0 is written here, 1 is carried forward, then again 3 1, then 1 1 it will become 1 is written here, then 1 is carried forward here, and then 1 1 we have to add 1 or 1, it will become 1 0. So next column there is no any value, so we have to write all the values, that is 1 0 1 1 is 1 0. So the resultant value will be 1 0 1 0 1 0, and which is equivalent to 42. If you add both the numbers, decimal numbers, it will become 42. Like this we have to do. Okay, see another example here. We are going to add 0 1 0 1 0 1 1 1 to 0 0 1 1 0 1 0 1. Okay, these two numbers we are going to add. Okay, see here. Okay, now equivalency is given here in decimal numbers. 1 1 will become 1 0, 0 is written here, 1 is carried forward. 1 1 become 1 0, 0 is written here, 1 is carried forward. Then 3 1 is come here, then it will become 1 1, 1 is written here, 1 is carried forward. So there is no other values and 1 is written directly here. And here 1 1 1 0, 0 is written, 1 is carried forward. 1 1 1 0, 0 is written here, 1 is carried forward. 1 1 1 0, 0 is written here, 1 is carried forward, and there is no other value, then 1 is directly written here. The equivalent number is given here, which will be equal to 140. Now see another number, a smaller number, 1 1 1 1 1 1 0. Okay, this is the equivalency. 1 0, 1 is written here, 1 1 1 0, 0 is written, 1 is carried forward. 1 1 1 0, 0 is written here, 1 is carried forward. 1 1 1 0, 1 0 is written. So it is the equivalency here. This is the example. If you want to add like this, you can do like this. Suppose we are going to give you another example. 1 1 0 1, and then 1 1 1, like this. Now we are going to add manually here. 1 1 will become 1 0, 0 is written here, so 1 is carried forward here. Then 1 0 0 1 0 1 means 1 1 we have to add, then it will become 1 0, 0 is written here, 1 is carried forward here. 1 1 1 3 1 is come here, then it will become 1 1, then 1 is written here, 1 is carried forward here, 1110 will become, this will be the answer, 10100 you can write like this, and this carried forward will be removed. Okay, like this we can do. Understood? Now see another example also given here, same process, same thing. Okay, see the example here, 0 1 1 1 1 1 0, 1 is carried forward, 1 1 1 0 0 is written, 1 is carried forward, 0 is written, 1 is carried forward, 0 is written, 1 is carried forward, and 1 is written. This is the equivalent. Now here see, this is the binary number with decimal values. Decimal meaning fractional values are there. So what is the equivalent value is given here, and see how we can do. There is nothing any other rule. Same rule will be applied for decimal binary numbers also. 1 1 become 1 0, 0 is written here, 1 is carried forward, 1 1 is become 1 0, 0 is written here, 1 is carried forward, 3 1 is come here, then 1 1 it will become 1 1 11, 1 1 1 is written here, 1 is carried forward, then 1 1 1 0, 0 is written here, 1 is carried forward, 1 1 1 0, 0 is written here, 1 is carried forward, 1 is written here. Now there is no problem. Same in the same way we have to add the decimal numbers having the fractional value, having the decimal value. Okay. Now we are going to understand another topic under this chapter, representing characters. Okay, representing characters. Previously we have learned that how integer numbers, unsigned integer numbers are represented inside the computer. Now here we are going to understand how characters, symbols are coded inside the computer. How they can represent. If we press a key from a keyboard A, then it will display A. How it is coded inside the computer, we can understand like this. Okay, there are 3 different types of coding which is used universally, that is ASCII, ISCII and Unicode. First of all, we will learn ASCII. It stands for American Standard Code. American Standard Code for Information Interchange. Note down, this abbreviation comes always in examination, so you have to remember this, learn this by heart, that what is the full form of ASCII? American Standard Code for Information Interchange. Now there are 2 types of ASCII. ASCII 7. ASCII 7 can represent 128 characters. 128 different characters means ASCII 7 means we have to take 7 ASCII digits, 7 binary digits, 1 1 1 1 1 1 and 1. If you convert this, if it is binary, then if we convert it in decimal, it will become 128 in decimal. So it can represent the 7 digits, 7 binary digit can represent total 128 different characters. Okay, different combinations. Out of 7 bits, what are those? Total 3 are zone bits. Okay, out of 7 bits, suppose you can understand like this. For letter A, in computer, in ASCII code, for value A, symbol A, the value is given like this: 1 0 0 0 0 and 0 and 1. Total how much? 1 2 3 4 5 6 7 digits. In ASCII 7, the symbol A is given a sequence number like this. Okay, total 7 digit, and if you convert this binary digit in decimal, it will become 65. So 65 is given for the ASCII A code. For B code, it is given 66 code. And it is like this: 1 0 0 0 0 1 0. Okay, then it is equivalent to 66. And similarly, for other symbols of alphabets, it is given the code like this. Okay, so in ASCII 7, first 3 bits are known as zone bits. This first 3 bit, okay, this first 3 bit is known as zone bit. Sorry, first 3 bit. this 100. The first 3 bit is 100 here. This is known as the zone bit, and other 4 are known as numeric bits. Other 4 are means 0, 0, 1, 0 are numeric bits. Okay, in ASCII 7 3 are zone bits and 4 rest digits are known as numeric bits. There is another version of ASCII is ASCII 8, and it can represent total 256 characters. If you convert total 8 digit of ASCII number of binary numbers, it will become 256 characters, and it is an extended form of ASCII 7, means it can represent total 256 different characters, which includes alphabets, capital alphabets, smaller alphabets, some symbols, some digits. All those things are represented using ASCII characters. Okay. Now come to ISCII. ISCII is the copy of ASCII, but it is made for Indian in the standard code for information interchange. It means a lot of efforts have gone into facilitating the use of Indian languages. To use Indian languages with computers like Hindi, Bangla, those languages, then for those languages a special type of information interchange code for computers is developed, that is known as ISCII, and its full form is Indian Standard Code for Information Interchange. This Indian language in computers, in 1991 the Bureau of Indian Standards adopted the ASCII. When it is adopted? In 1991, and it is an 8-bit code. There is no version of ASCII. In ASCII there are 2 versions, ASCII 7 and ASCII 8, but in ISCII there is only one version, that is ASCII 8-bit code, which allows English and Indian scripts alphabets to be used simultaneously. Means English and Indian scripts both we can use with this ASCII code. Characters coded in ASCII need 8 bits for each character, means total 8 bits is needed to code each character. 8 bits it is needed. Means say for example for letter A, in ISCII is required 8 bits. How much? 8 bits, and those bits are 0, 1, 0, 0, 0, 0, 0 and 1. Total 8 bits, which is again equivalent to 65. In ISCII this is like this. Okay, and for other letters, suppose the Hindi letter ko, okay, ko, this may be some code, okay, and total 8 digits, binary digits is used for that letters. Okay, so many letters are there, Indian characters are there already encoded in Indian Standard Code. Now we are going to learn Unicode. Actually, what happened? ASCII code, the first one, this ASCII code is used with computers only to represent English alphabets. So different countries develop their own codes. As for example, Indian has developed their own code to understand their own characters, the local characters, that is the Hindi or English, like this they developed ISCII. Similarly, some other countries also developed their own codes for their computers, and this generates some problems when exchanging information. Suppose we want to send some information from Indian country to another country, okay, and those Indian used ISCII to code their alphabets in computers, then the message when goes to some other country, they are not readable, they cannot understand because they don't have those ASCII code there, or they have to install those ASCII code, then only they can understand the code. Okay, there is lots of problem happening between different countries, okay, so because all countries have developed their own codes and exchanging of information become troublesome. So Unicode is developed to remove those problems, those remedies, Unicode is developed. Unicode is a new universal coding standard. Full form is Universal Coding Standard by all new platforms. It is promoted by Unicode Consortium. Actually, a committee is an organization is developed, non-profit organization, which is known as Unicode Consortium. Okay, this developed this Unicode. This organization helps to develop this Unicode so that each country can use a same code for their data. Now, Unicode provides a unique number for every characters irrespective of the platform, program, and the language. Okay, total language barriers, platform barriers, program barriers have been demolished, and a single code system is developed, that is Unicode. Now you can see that we can use Facebook, okay, WhatsApp, and we can represent any characters. Even we can write Hindi, English, Arabic, Urdu, or Bangla, any language we can use using those apps. Because how it is possible, how it become possible with the use of Unicode coding system, and whole world use the same code. There no information exchange becomes easier and understandable. It is a character coding system designed to support the worldwide interchange, processing and display of the written text of the diverse languages. So many languages can be used. Okay, this is known as Unicode, Universal Coding System. It is a generalized coding system to use with the whole world. Okay, irrespective of the platform. Platform means if they are using Apple computers, they can use Unicode. Okay, if they are using Android, if they are using Windows, there is no there is no problem, there is no barrier. Okay, so anyone can send their messages and they can be understood by any different platforms, programs, softwares. Okay, now this chapter is finished and we have come to exercises. Now we have to do these exercises, and very easy exercises. You must do these exercises. Now thank you all of you.